Welcome to late space, where the cosmos unfolds slowly and science becomes a journey rather than a destination. Tonight we're venturing into one of astronomy's most captivating enigmas, a mystery that has puzzled scientists for nearly a century and continues to reshape everything we thought we understood about reality itself. We're going to explore dark matter, the invisible substance that appears to compose most of the universe's mass, holding galaxies together and shaping the very structure of space itself. Before we begin this exploration, I wonder where you are right now. Perhaps you're settled into bed with the day finally behind you, or maybe you're watching the evening fade into twilight with some quiet time carved out just for yourself. Wherever you find yourself, you're floating through the same cosmos we're about to discuss, surrounded by mysteries that dwarf anything we can fully comprehend. The strange truth is that when you gaze upward on a clear night, the glittering stars and luminous galaxies represent merely a fraction of what actually exists. The rest, the far greater portion, remains completely invisible to us. If current scientific understanding proves correct, this hidden ocean of matter outweighs everything we can observe by more than 5 to 1. Consider that for a moment. The shining celestial objects that have inspired humanity since the beginning of recorded history make up only the visible edge of something vastly larger and fundamentally different. If you're finding value in this slow, contemplative approach to cosmic mysteries, if the idea of exploring science at a pace meant to calm rather than excite resonates with you, I'd genuinely appreciate it if you'd consider subscribing or sharing this with someone who might appreciate a peaceful moment at day's end. It helps this channel reach others searching for the same kind of gentle refuge. So find a comfortable position. Let your breathing settle into a natural rhythm. Release whatever tensions the day has accumulated, because tonight we're embarking on a journey through one of the most profound mysteries science has ever encountered. We'll move through the evidence carefully, examine the implications thoughtfully, and explore the strange possibilities this mystery presents, not rushing toward conclusions, but simply allowing curiosity to guide us forward. The problem that wouldn't disappear. Dark matter. The very phrase sounds like something from science fiction, like a plot device in a story about hidden dimensions or parallel realities. Yet the name represents something fundamentally real, a genuine puzzle that observation after observation has confirmed beyond reasonable doubt. Picture a spiral galaxy in your mind, one of those magnificent structures captured in telescope photographs. Arms of starlight curve gracefully outward from a brilliant centre, creating patterns that resemble cosmic whirlpools frozen in time. These images are among the most beautiful that astronomy produces, showing us island universes separated from our own by incomprehensible distances. Here's the problem that astronomers discovered. When you calculate the mass contained within all those visible stars, all that glowing gas and dark dust lanes, and then determine how fast the galaxy should be rotating based on that mass, the numbers don't work. The galaxy spins too rapidly. Think of it this way. The stars at a galaxy's outer edges orbit around the galactic centre at speeds that should send them flying off into intergalactic space, like stones released from a spinning sling. The visible mass simply doesn't provide enough gravitational attraction to hold them in place, and yet they remain. Orbit after orbit, generation after generation, the stars stay bound to their galaxies. The only way this makes sense, according to our understanding of gravity, is if galaxies contain far more matter than we can detect through telescopes. Something invisible must be providing the additional gravitational pull required to keep these systems intact. That something is what astronomers call dark matter. It's not dark in the conventional sense, the way a shadow is dark or how space appears dirty between stars. Dark matter doesn't absorb light the way dust does. It doesn't glow faintly like cooling embers. It simply doesn't interact with electromagnetic radiation at all. Light passes through or around it as though it barely exists, which is precisely why it took so long for scientists to realize it was there. But gravity reveals its presence. gravity is the one force that dark matter cannot hide from, the one interaction that betrays its existence. Through gravity's effects on visible matter, we've learned that most of the universe consists of this hidden substance. By most, I mean the proportion is staggering. Current measurements suggest that for every kilogram of ordinary matter, the stuff that makes up stars, planets, your own body, there exist more than 5 kilograms of dark matter. All the familiar atomic matter in the cosmos, everything built from protons, neutrons and electrons, represents only about 17% of the total matter. The remaining 83% is this mysterious invisible component. It's almost amusing when you think about it. Humanity spent millennia mapping the heavens, charting star positions, cataloguing galaxies, building increasingly powerful telescopes to see deeper into space. Only within the last century did we discover that everything observable represents a minority of what actually exists. It's comparable to spending years carefully arranging furniture in a room, only to discover the room itself floats on an invisible ocean you never knew was there, an ocean that's larger, more massive, and more fundamental than the furniture you thought represented everything. The first hints emerged in the early decades of the 20th century. Astronomers measuring the velocities of galaxies within galaxy clusters noticed something peculiar. The galaxies moved as if held together by far more gravitational attraction than their visible stars could possibly provide. Later, in the 1970s, Vera Rubin and her colleagues conducted detailed measurements of individual galaxy rotations and found the same pattern. Stars on the galactic periphery circled much too, quickly. Additional mass had to be present, mass that didn't emit any detectable light. Rubin's meticulous observations made the case impossible to dismiss. Something invisible, something non-luminous, was definitely there. And it wasn't a minor component or a small correction to existing models, it was the primary ingredient. At this stage, you might wonder what scientists have wondered for decades. What exactly is this substance? Could it be some form of hidden matter made from familiar particles, perhaps faint stars we can't detect or clouds of cold gas? Or does it represent something entirely new, particles beyond those we've discovered so far? These questions form the foundation of modern cosmology's greatest challenges. The answers remain frustratingly out of reach, despite decades of intensive research. But before we explore possible explanations, let's sit with the strangeness a bit longer. Because sometimes the most profound insights come not from rushing towards solutions, but from fully appreciating the depth of a mystery, a universe mostly invisible. You exist in a universe where the overwhelming majority of matter is invisible to human senses. Not invisible in a metaphorical sense, but truly non-interacting with the electromagnetic radiation that makes vision possible. The atoms composing your physical form, the ones creating your skin, bones, and every cell, belong to the small visible fraction. You represent luminous matter. You're part of the rare portion that interacts with light. Everything around you that you can see or touch exists within this tiny minority. The remainder of the universe, the silent majority, drifts invisibly around galaxies, connecting them into vast cosmic filaments, like some enormous three-dimensional spider web. When you observe the Milky Way stretching across a dark sky, you're seeing the bright decorative elements arranged on a much larger invisible framework. Without that framework, the stars wouldn't occupy those positions, galaxies wouldn't form in their familiar structures, planets wouldn't orbit stars, you wouldn't exist to contemplate these questions. Dark matter, silent and hidden, made the visible universe possible. The term itself, dark matter, functions more as a placeholder than a true description. It tells us just two things with certainty. First, it possesses mass, enough to create significant gravitational effects. Second, it doesn't interact with electromagnetic radiation in ways we can detect. That's it. Two pieces of information. From these two facts, an entire field of scientific investigation has emerged. Underground laboratories carved into mountains shield detectors from interference. Massive particle accelerators smash protons together at velocities approaching light speed. Telescopes map how distant galaxy shapes distort as invisible mass bends their light on the journey to our instruments. All of this effort chases a quarry that has never revealed itself directly, yet evidence accumulates from every direction. Galaxies, galaxy clusters, the large-scale structure of the cosmos, all make sense only if this unseen matter exists in abundance. Computer simulations of cosmic evolution that exclude dark matter simply cannot reproduce the universe we observe. They produce results that look nothing like reality, but include the invisible ingredient in those simulations, and suddenly the virtual universe resembles the real one. Filaments and clusters appear exactly where observations find them. It's as though we've been given a recipe for creating the cosmos, but are still missing the name of the main ingredient. Sometimes scientific progress works this way. You know something exists not because you observe it directly, but because everything else points unmistakably toward it. Like hearing music playing in another room with the door closed, you know someone must be performing it. Dark matter is the music behind the closed door of the universe. We've been standing outside listening for nearly a century, so here we stand at the threshold of one of science's greatest mysteries, the invisible mass that outweighs all visible stars, the silent architect of galactic structure, the substance that shapes the cosmos while refusing to reveal what it actually is. As we continue forward, we'll trace the history of how astronomers discovered it, examine the experiments designed to detect it directly, and explore the strange possibilities it raises about reality's fundamental nature. Perhaps as you listen, you'll experience the same odd comfort many scientists admit to feeling, that even facing what we don't know, even in mystery's presence, there's something steadying about acknowledging it honestly. We don't possess all the answers, but we have compelling questions, and those questions themselves provide sufficient guidance for tonight's journey. Let those questions be the gentle current carrying us forward. What we see is not what is. When you look upward on a clear night, you observe a canvas scattered with light points. To the unaided eye, perhaps a few thousand stars become visible from even the darkest locations. Through a telescope, that number expands dramatically, revealing that the sky isn't sparsely populated but overwhelmingly filled with distant suns. Each star we observe belongs to our galaxy, the Milky Way, which itself represents merely one among hundreds of billions. From Earth's surface, light travels across space to reach our eyes, and it feels natural to assume that the universe we observe is the universe that exists. After all, vision has always been humanity's most trusted sense. We depend on it to navigate, to recognize each other, to understand the world. So it seems intuitive that the stars and galaxies glowing brilliantly represent the universe's actual contents. But the truth is that our eyes reveal only a fraction of what really exists. That realization, unsettling though it may initially sound, represents one of the most profound shifts in human understanding. The objects we can see, touch, and measure directly form only the visible portion of a much larger cosmic structure. Beneath that glowing surface lies something darker, something more substantial, the hidden matter that shapes everything yet remains beyond sight's reach. For most of history, humans had no reason to suspect this imbalance. The night sky, though mysterious, seemed straightforward enough. Stars shone because they burned fuel. Planets reflected sunlight. Comets streaked briefly across the darkness and disappeared. Everything visible could be explained through natural processes that, while not always fully understood, at least followed from the familiar principle that objects make themselves known through light. If you couldn't see something, perhaps it simply wasn't there, or at least it wasn't relevant to daily existence. That assumption worked adequately for centuries. The telescope's invention expanded vision's boundaries but reinforced the same basic idea. Galileo's instrument revealed lunar craters, moons orbiting Jupiter, countless faint stars invisible to the naked eye. Later, larger telescopes revealed galaxies, nebulae, and clusters. Each advance in optical technology seemed to confirm that the universe was simply a larger and more varied version of what we already knew. The brighter your instrument, the more of reality you could capture. Seeing equaled knowing. But in the 20th century, cracks began forming in that comfortable belief. Astronomers measuring galactic motions discovered that luminous matter alone couldn't explain their behavior. What was visible, even when multiplied by billions, proved insufficient. The mass we could see was merely a fraction. The invisible remainder had to exist, or galaxies would tear themselves apart. To appreciate the problem's scale, consider this calculation. If you sum up all the stars, gas clouds, and dust in a typical galaxy, and use their combined mass to calculate expected gravitational pull, you derive a specific prediction for how stars should orbit around the galactic centre. Close to the core where most mass concentrates, stars should orbit rapidly. Moving outward where less mass is enclosed, orbital speed should drop, just as planets in our solar system slow down with increasing distance from the Sun. Mercury completes its orbit in merely 88 days, while Neptune requires 165 years for a single circuit. That makes intuitive sense because gravity weakens with distance. But galaxies don't follow this pattern. Measurements demonstrate that stars far from the galactic centre orbit just as quickly as stars much closer in. It's as though the galaxy refuses to thin out gravitationally. The outer regions that should be loose and drifting are instead firmly held. The only explanation is that enormous amounts of unseen mass surround the galaxy, forming a vast halo extending far beyond the visible spiral arms. Without this halo, stars would escape. With it, the galaxy remains intact, so what we can see is not what actually is. The luminous disk of a galaxy, beautiful as it appears, represents only visible decoration. The true mass lies in the unseen halo, enveloping the system in an invisible gravitational sphere. This realization overturns natural intuition. We're biologically wired to trust vision. Yet vision, it turns out, provides an unreliable guide to the universe's actual structure. It shows only the minority component. Scientists now estimate that all ordinary matter, the stuff constructed from atoms, contributes only about 5% of the universe's total contents. 5%. That includes stars, planets, interstellar gas, intergalactic dust, black holes, and every atom in your physical body. The rest is invisible. Roughly 27% is dark matter, and approximately 68% is something even stranger called dark energy, which drives the universe's accelerating expansion. But dark energy is a mystery for another time. For now, it's sufficient to recognize that most of what holds the cosmos together lies beyond sight. It's natural to ask how we know this if we can't see it. The answer is that science doesn't rely solely on vision. We measure through inference, through consequence, through the footprints left on what we can observe. Light bends when passing near massive objects, a phenomenon Einstein's general relativity predicted, and observations have confirmed countless times since. By mapping how light from distant galaxies distorts, astronomers create maps of invisible matter. They observe vast regions where no stars shine yet, where gravity bends light just the same. These invisible clumps and filaments weave the universe's large-scale structure, guiding galaxy and cluster formation like scaffolding beneath a building. In some regions, the evidence is dramatic. Consider the Bullet Cluster, a collision between two galaxy clusters observable in X-rays and visible light. The hot gas, which should dominate the mass, lingers in one region, but gravitational lensing indicates most mass lies elsewhere, separated from the gas. This mismatch demonstrates that something other than normal matter must be present, carrying most of the weight. Astronomers point to it as one of the clearest visual proofs of dark matter's existence. The contrast between what we can see and what we cannot also extends closer to home. Within our own Milky Way, The distribution of stars suggests an invisible halo approximately 10 times more massive than all visible matter combined. This halo stretches far beyond the disk, enveloping our galaxy in a spherical cloak of unseen mass. Though we move through it constantly, we experience no direct sensation of it. It doesn't push against us, doesn't block sunlight, doesn't interact with atoms in ways our senses can detect. Yet its gravitational influence is undeniable. The solar system itself is merely a speck within this halo, like a small bubble suspended in a vast invisible ocean. To live in such a universe requires accepting a humbling truth. What is visible is not what is dominant. We inhabit the minority slice, illuminated and comprehensible, while the bulk of reality remains hidden. This doesn't mean the visible universe is unimportant. It is, after all, the part that gave rise to life, to consciousness capable of wondering, to technology enabling us to probe deeper. But it's not the complete story. It's only the bright fringe of a much larger tapestry, the weight of the invisible. When you think about weight, you naturally imagine something tangible. A heavy bag in your hands, a suitcase that feels too heavy at airport check-in, or the reassuring pull of gravity when you sink into your favourite chair at day's end. Weight belongs to things we can hold, touch, measure with scales. It's something that presses downward, something that announces its presence clearly. In everyday life, weight always connects to matter you can see. But in the universe, weight has a far broader meaning. Gravity responds to all mass, visible or not. And in that sense, the cosmos is revealing a strange truth. The universe is heavier than it appears. Astronomers discovered this not by chance, but by observing carefully. They studied how galaxies move, how galaxy clusters behave, how light bends on its journey across space. Repeatedly, measurements reveal the same story. There is more mass than meets the eye. The luminous stars, glowing gas clouds, and delicate streams of dust compose only a small part of the whole. Something unseen carries the majority of the weight, shaping the universe with its gravity. To appreciate the scale of this discrepancy, imagine totaling every star in the Milky Way, perhaps 400 billion of them, and calculating their combined mass. Now include all the gas between stars, the clouds of hydrogen and helium stretching for light years, as well as the dust filtering starlight and the black holes hidden in stellar remnants. When you tally all of that, you arrive at an impressive number, one that defines the visible skeleton of our galaxy. But when you compare that to the total gravity holding the Milky Way together, you find you're short by a factor of about 10. 10 times more matter is required to explain the galaxy's weight. That missing matter, though invisible, outweighs the visible by a wide margin. This is not a small correction or a minor oversight. It's not as though a few dim stars escaped detection or some hidden gas clouds went unnoticed. The discrepancy is overwhelming. The invisible matter dominates. It's the main contributor to the galaxy's mass. What we can see is almost ornamental compared to the vast halo of unseen material surrounding us. The same is true on larger scales. Clusters of galaxies, which are among the most massive structures in the universe, reveal their hidden weight in dramatic ways. The galaxies within them move at speeds far too high to be bound by visible matter alone. Yet the clusters remain intact. Something must be providing the gravitational adhesive, and that something is dark matter. Even the hot gas filling spaces between galaxies, glowing in X-rays, cannot account for the binding mass. Once again, the majority is invisible. One of the most striking demonstrations of this hidden weight comes from gravitational lensing. According to Einstein's general relativity, mass bends space-time, and light follows the curves of that space-time. When distant, galaxies lie behind massive clusters. Their light is bent and distorted, creating arcs and multiple images. By measuring the degree of bending, astronomers can map the mass distribution of the cluster. Again and again, these maps reveal mass concentrated where no luminous matter exists. The weight is real, measurable, and undeniable, but invisible to our eyes and instruments that rely on light. The term dark in dark matter can mislead. It suggests gloom, shadow, or even something sinister. In reality, dark simply means invisible to light. It doesn't glow, doesn't absorb, doesn't scatter. It passes silently through electromagnetic interactions, leaving no trace except gravitational effects. And gravity has been more than enough to reveal its immense contribution. The invisible weight also affects the universe's very history. Shortly after the Big Bang, matter and radiation were intertwined in a dense hot plasma. As the universe expanded and cooled, atoms formed and light decoupled from matter, creating the cosmic microwave background radiation we still detect today. The patterns in this radiation, tiny temperature ripples across the sky, carry information about mass distribution in the early universe. Analysis of these patterns shows that ordinary matter alone couldn't have formed the structures we see today. Without the additional gravitational pull from dark matter, galaxies wouldn't have formed quickly enough. The invisible weight acted as scaffolding, drawing ordinary matter into clumps and allowing stars and galaxies to ignite. In this way, dark matter is not just an addition, not just an extra ingredient. It's essential to the cosmic story. Without it, the universe would look nothing like it does. There would be no galaxies, no stars, no planets, and no listeners here tonight contemplating their place in the cosmos. The invisible weight is not optional, it's fundamental. And yet, for all its importance, we don't know what it is. Scientists propose candidates from exotic particles with names like WIMPs, weakly interacting massive particles, to axions to sterile neutrinos. Each candidate attempts to explain how something can have mass, yet remain invisible to light. Experiments buried deep underground or placed in remote laboratories seek the faintest whisper of interaction. Giant detectors filled with noble gases shielded from cosmic rays sit in silence, waiting for the rare possibility that a dark matter particle might collide with an ordinary atom. So far, the silence continues. This doesn't mean the search is hopeless. In science, persistence is everything. The invisible weight leaves its imprint everywhere, in galaxies and clusters in the cosmic background. It cannot be ignored. Each piece of evidence confirms that something massive exists beyond our vision. Finding its identity is one of the central quests of modern physics. The glue of the cosmos. If you've ever built something, you know the importance of a good adhesive. A puzzle stays together with patience and careful alignment. But a house, a bridge, even a child's craft project often needs something that binds the pieces into one whole. In the universe, stars and galaxies need that too. Left on their own, they would not remain the intricate structures we admire in telescope images. They would drift apart, the pieces scattering into the void. Yet they don't. They hold. Something acts as the adhesive. Not a sticky liquid, not nails or screws, but a force, a presence. That presence is gravity. And gravity is strengthened, shaped, and given its full power by the unseen mass we call dark matter. To understand how essential this glue is, it helps to return to the simple concept of a spinning galaxy. Imagine a merry-go-round filled with children spinning faster and faster. The children near the centre hang on easily because the pull toward the middle outweighs the tendency to fly outward. But those at the edge struggle. The faster the spin, the harder it becomes to hold on. Now scale that image up to something millions of light-years across. Stars orbiting the edges of a galaxy spin at speeds that should hurl them outward into the blackness. Yet they remain, orbit after orbit, generation after generation of stars bound by gravity that exceeds what visible matter alone could provide. The invisible weight supplies the glue, and without it the galaxy would unravel. This glue is not unique to a single galaxy. It binds clusters of galaxies, the largest gravitationally bound structures in the cosmos. These clusters, containing hundreds or even thousands of galaxies, should be unstable if only visible matter counted. The galaxies move at speeds too high for the light we see to explain. But when dark matter is included, the system makes sense. The invisible halos around galaxies and clusters act like enormous cushions of gravity, keeping the luminous matter gathered and stable. The idea of a glue holding the universe together is both simple and astonishing. Simple because the concept of a binding agent is something we encounter in daily life. Astonishing because in the universe that agent is made of something we cannot see or touch. It exists only through its gravitational influence. It doesn't shine, doesn't glow, and yet it's stronger than everything that does. One of the most remarkable demonstrations of this cosmic glue comes from examining the early universe. After the Big Bang, the cosmos was a hot, dense soup of particles and radiation. Matter and light were coupled together, constantly scattering, preventing the formation of stable structures. As the universe expanded and cooled, light decoupled from matter, leaving behind the cosmic microwave background radiation. This ancient light still reaches us today, stretched into microwaves by billions of years of expansion. But embedded in it are tiny variations, ripples in temperature reflecting the distribution of matter at that time. Those ripples tell a story. Ordinary matter alone would not have clumped quickly enough to form galaxies and stars in the time available. The glue of gravity from dark matter was necessary to seed the structures. It provided the scaffolding, the invisible wells into which ordinary matter fell. Without that extra gravity, the luminous universe would not have emerged. The stars and galaxies we see today are decorations placed on the framework built by dark matter. The cosmic glue shaped everything. In many ways, this glue is more reliable than the visible matter it binds. Stars live and die, burning fuel until they collapse or explode. Gas clouds condense and disperse. Planets form and eventually crumble. The luminous universe is in constant flux, restless and changing, but the halos of dark matter endure. They extend beyond the flickering lives of stars, shaping galaxies over billions of years. They provide the long-term stability that visible matter cannot. It's strange to think that something so invisible can also be so permanent. We're accustomed to associating permanence with the tangible. A stone feels solid, enduring. A mountain seems eternal compared to the fleeting life of a flower. Yet in cosmic terms, even mountains wear away. Stars collapse, galaxies merge. The dark matter, invisible though it is, carries on. It holds not through brilliance, but through persistence. Scientists often illustrate this by running simulations. They input the laws of physics, the expansion of the universe, the known amounts of visible matter, and then add dark matter. When they let the simulation run, starting from the smooth distribution of the early universe, something beautiful emerges. Filaments form, long strands of invisible matter connecting into a cosmic web. Along these strands, galaxies gather like beads, clusters form at intersections, and the universe grows into the structure we observe through telescopes. If they leave out the dark matter, the simulation fails. Galaxies do not form, clusters do not exist, the web never appears. The glue is essential. Those who first notice science often begins with someone noticing something that doesn't quite fit. A number that's out of place, a measurement that resists explanation, or a pattern that refuses to behave the way expectations say it should. The story of dark matter is no different. It began not with a sweeping theory or a bold prediction, but with astronomers who looked carefully at the sky and realized something wasn't adding up. One of the earliest names in this story is Fritz Zwicky, a Swiss astronomer working in the 1930s. Zwicky was not the type to mince words. He was brilliant, outspoken, and occasionally abrasive, known for giving colleagues unflattering nicknames. But his sharp tongue was matched by a sharp mind, and it led him to one of the great insights of 20th century astronomy. Zwicky was studying the Coma Cluster, a collection of galaxies bound together by gravity. By measuring how fast the galaxies moved within the cluster, he could estimate the total mass required to hold the cluster together. What he found was astonishing. The galaxies were moving far too quickly. If the only mass present was what could be seen in telescopes, the cluster should have flown apart. Yet it remained bound. The conclusion was inescapable. There had to be much more mass than what was visible. Zwicky called this missing mass dunkle Materie, German for dark matter. At the time, his claim was bold and not widely embraced. The idea of invisible matter dominating the universe seemed far-fetched, and many colleagues dismissed it as speculation. Zwicky himself didn't always make it easy for others to agree with him. His blunt style, while effective in pushing boundaries, sometimes alienated potential allies. Still, his measurements were there in the data. He had seen something extraordinary, the first strong hint that most of the universe might be invisible. For decades, Zwicky's idea lingered in the background, neither fully accepted nor entirely forgotten. Astronomers continued to measure galaxies and clusters, but the focus was often on other questions. It wasn't until the 1970s that the missing mass mystery gained undeniable weight, thanks to the meticulous work of Vera Rubin. Rubin was an American astronomer whose career began at a time when women in science faced enormous obstacles. Opportunities were scarce, recognition even scarcer. She pursued astronomy anyway, driven by curiosity and persistence. By the time she turned her attention to galaxies, she had already built a reputation for careful, thorough work, and it was that care that allowed her to see what others had overlooked. Rubin, working with Kent Ford, developed precise methods for measuring galaxy rotation. They used powerful spectrographs to track the motion of stars at various distances from the galactic centre. The expectation was simple. Stars closer to the centre should orbit quickly, while those farther out should slow down just as planets in our solar system do. The Sun holds most of the solar system's mass, so the farther a planet is, the weaker the pull and the slower the orbit. Astronomers assumed galaxies would follow the same pattern, but Rubin's data told a different story. The stars at the edges of galaxies did not slow down. They orbited just as quickly as stars near the centre. The rotation curves, instead of declining with distance, remained flat. The only explanation was that galaxies contained far more mass than was visible. Something unseen was providing the extra gravity needed to keep those outer stars in place. Rubin's work was revolutionary, not only for what it revealed, but for how solid the evidence was. She'd gathered careful, repeatable data from many galaxies, and the pattern was consistent. Flat rotation curves became one of the strongest pieces of evidence for dark matter. Unlike Zwicky's earlier claims, Rubin's results could not be easily dismissed. The invisible mass was not a quirk of a single cluster. It was a universal feature of galaxies. Rubin herself spoke about the experience with both humility and humour. She once remarked that she had expected to find declining rotation curves, and when she didn't, she thought she must have made a mistake. But as the data piled up, the conclusion became unavoidable. Something enormous and invisible was shaping galaxies. The cosmos was telling her a story, and she listened. Shadows in the starlight. When you step outside on a clear night and look at the stars, it's easy to believe that what you see is all there is. The pinpoints of light seem complete in themselves, each one shining steadily against the dark backdrop. But just as a shadow tells you something about the object casting it, the stars tell us something about what lies unseen. Their motions, their arrangements, their collective dance across the sky reveal that they are not moving alone. Something accompanies them, invisible yet powerful, guiding their paths like an unseen partner in a dance. These shadows in the starlight are the fingerprints of dark matter. Astronomers do not detect dark matter by looking directly at it, because it leaves no glow on a telescope's image. Instead, they watch how stars behave. They track the orbits of stars within galaxies, the motion of galaxies within clusters, and the distortions of light from galaxies far beyond. Each of these observations carries the signature of something massive yet invisible. It's as if the starlight itself is casting shadows, revealing what cannot be seen directly. Consider again the rotation curves of galaxies, the measurements that Vera Rubin and her colleagues made so carefully. Stars near the centre of a galaxy orbit quickly, held tight by the gravity of the dense core. If only visible matter existed, stars farther from the centre should slow down, just as planets far from the Sun orbit more slowly than those close in. But the stars on the edges do not slow. Their speeds remain constant even as distance increases. That flat curve is the shadow, the unmistakable sign that unseen mass surrounds the galaxy. Without it, the edges would unravel. With it, they hold. The same kind of shadow appears on larger scales. In clusters of galaxies, the galaxies move as though bound by a mass far greater than what can be seen. The hot gas that fills the cluster, glowing in X-rays, adds to the visible total, but even combined, stars and gas are not enough. The galaxies would escape if only those masses were present. The fact that they remain bound is the shadow, the silent testimony of dark matter holding them together. Perhaps the most striking shadows of all come from the bending of light itself. According to Einstein's theory of general relativity, massive objects warp the fabric of space-time. Light travelling through this curved space bends, much as a ball rolling across a warped surface will change direction. This bending is known as gravitational lensing, and it provides one of the most powerful tools for detecting invisible mass. When astronomers observe distant galaxies whose light passes through massive clusters on its way to us, the images appear distorted. Some stretch into arcs, others appear doubled or even multiplied. By carefully analysing these distortions, astronomers can map the distribution of mass in the intervening cluster. Time and again, these maps reveal mass concentrated in regions where no visible matter exists. The light itself carries the evidence. The starlight, bent and twisted, reveals the shadows of invisible halos. One particularly famous example is the Bullet Cluster. This system is the aftermath of two galaxy clusters colliding at tremendous speeds. The hot gas from the clusters interacted, slowed, and piled up in the middle, visible in X-ray images. But when astronomers mapped the gravitational lensing, they found the bulk of the mass was not where the gas was. It had passed through with the galaxies, continuing outward. This separation of visible matter and gravitational mass provides one of the clearest demonstrations that dark matter is real. The shadows in the starlight are undeniable, the expanding universe's secret passenger. The universe itself is moving, not in the way a planet or star drifts, not like a comet tracing an arc across the sky, but in a far larger sense. Space itself is stretching. The galaxies are not flying through a fixed void like ships across an ocean. The ocean itself is swelling, carrying them apart. This expansion, discovered in the 20th century, reshaped our entire picture of the cosmos. It told us that the universe has a history, a beginning, and that it is still unfolding. But what often goes unspoken is that this expanding universe has a hidden companion, a secret passenger riding along with the galaxies, quietly shaping their fates. That passenger is dark matter. To see how the invisible joins this journey, it helps to step back to the 1920s, when astronomer Edwin Hubble made a startling discovery. By measuring the light from distant galaxies, he found that almost all of them were redshifted, meaning their light was stretched to longer wavelengths as they moved away. The farther away a galaxy was, the faster it seemed to recede. This was not the result of a central explosion sending galaxies outward, but the stretching of space itself. The fabric of the universe was expanding, and every galaxy was being carried along. At first glance, dark matter might seem irrelevant to this grand motion. After all, expansion concerns the geometry of space and the influence of dark energy, the mysterious driver of accelerated growth. But dark matter has been present from the very beginning, and its gravity has played a crucial role in how the expansion shaped structure. Without it, the universe would have expanded into emptiness, a smooth sea of matter too evenly spread to form galaxies or stars. In the earliest moments after the Big Bang, matter and radiation were coupled together in a dense, hot plasma. Tiny fluctuations in density, minute differences of 1 part in 100,000 were present, like faint ripples on a pond. On their own, these ripples might not have grown. Radiation pressure from light kept pushing against the clumping of ordinary matter, smoothing it out. But dark matter was different. It did not interact with light. It was free to clump under gravity even while radiation held ordinary matter at bay. As the universe expanded and cooled, these clumps of dark matter grew. They became the seeds of structure, the gravitational wells into which gas and stars would eventually fall. When light finally decoupled from matter, about 380,000 years after the Big Bang, leaving behind the cosmic microwave background, the scaffolding of dark matter was already in place. Ordinary matter could now settle into these wells, forming galaxies and clusters. Without dark matter riding as a hidden passenger through expansion, the luminous universe would not exist. Galactic whirlpools. When you think of galaxies, it's hard not to picture them as spirals. The great pinwheel shapes captured in telescope images are some of the most striking sights astronomy has to offer. Arms of starlight curve outward from bright centres, winding like whirlpools frozen in space. Some are symmetrical, others more ragged, but all of them share a sense of motion, a swirling balance between gravity and momentum. It's no coincidence that these vast whirlpools became one of the clearest clues to the universe's hidden mass. In the way they spin, they carry the signature of something invisible holding them together. A galaxy, despite how it looks in pictures, is not a flat painting on the sky. It is a three-dimensional system, billions of stars orbiting around a common centre, along with gas, dust and dark matter. Each star follows its own path, guided by the collective gravity of the system. The result, when seen from far away, is the spiral pattern, arms made of stars, that seem to stream outward like ripples in water. But beneath that graceful shape lies a problem that puzzled astronomers for decades. The whirlpool spins too fast. If only the visible matter in a galaxy existed, the stars on the edges would be in danger of flying off. Think again of a merry-go-round in a playground. The children near the centre can hang on easily, but those at the edge feel the strongest pull outward, the centrifugal force threatening to send them flying. In a galaxy, the pull inward comes from gravity supplied by the mass inside the star's orbit. The more mass enclosed, the stronger the pull. Close to the galactic centre, the mass is large, so the stars orbit quickly. Farther out, the enclosed mass should level off, and the stars should orbit more slowly, just as planets in the solar system move slower the farther they are from the Sun. But galaxies do not behave that way. Vera Rubin's careful measurements in the 1970s showed that the rotation curves of galaxies are flat. The stars far from the centre orbit just as quickly as those closer in. The whirlpool does not thin out. The spiral arms remain held together, bound more tightly than visible matter can explain. It is as if an invisible halo surrounds the galaxy, providing the extra gravity needed to keep the whirlpool intact. Without that hidden mass, the spiral arms would unravel. Light's journey through curved space, light has always seemed like the purest messenger. It travels across space at the fastest speed nature allows, carrying with it images of the distant universe. A telescope is essentially a net for catching this light, letting us see stars, galaxies and nebulae as they were when the light first left them. For centuries, astronomers treated light as a straight traveller, moving along invisible lines from source to eye. But in the 20th century, Einstein's theory of general relativity changed that picture forever. According to relativity, space itself can curve, and light, which always follows the straightest possible path, must bend along those curves. This prediction seemed exotic at first. The idea that space could be warped by mass was not something people were used to imagining. Yet the first test came quickly. In 1919, during a solar eclipse, astronomers observed stars near the Sun appearing slightly shifted in position. Sun's gravity had bent their light on its way to Earth. It was a small effect, but it confirmed Einstein's theory and introduced the concept of gravitational lensing, the bending of light by gravity. Gravitational lensing is more than just a curious side effect of relativity. It has become one of the most powerful tools for understanding the universe. It allows us to measure mass in a way independent of light. Wherever light bends, mass must be present. And when astronomers apply this tool, they find again and again that there is more mass than what is visible. Gravitational lensing reveals the hidden scaffolding of dark matter, making it one of the clearest demonstrations of the invisible universe. The cosmic web. When people first began to map the sky, they thought of stars as scattered points, each one distant but largely isolated. Even when galaxies were recognized as their own systems, they were often imagined as islands in the void, drifting alone through space. But as the ability to survey the universe grew, a new picture emerged. Galaxies were not random. They were arranged in patterns, stretched into filaments and sheets, clustered into knots, leaving behind vast empty spaces between them. On the larger scales, the universe is not an even mist of galaxies, but a web, intricate and interconnected, stretching across billions of light years. And the strands of this web are woven not from starlight, but from dark matter. The discovery of this structure came gradually as telescopes and surveys expanded their reach. In the mid-20th century, astronomers noticed that galaxies tended to cluster together rather than distribute evenly. Some regions of the sky were rich with galaxies, while others seemed almost empty. As computers grew powerful enough to simulate cosmic evolution, the picture became clearer. The universe, starting from tiny fluctuations after the Big Bang, grew into a vast network. The filaments we see today are the result of dark matter collapsing under gravity, pulling ordinary matter along with it. One way to imagine it is to think of a spider's web covered in dew. The strands of the web are mostly invisible until the droplets cling to them, catching the light. In the universe, dark matter forms the strands, unseen and pervasive. Galaxies are the dewdrops, glowing along the filaments. Without the web, the drops would be scattered randomly. With it, they're arranged into an organized, interconnected pattern. The cosmic web is not just a poetic image. It is the literal architecture of the universe, not made of stars. When you look up at the night sky, the natural assumption is that everything up there must be made of the same stuff as the stars. The bright points of light are suns, the hazy patches are collections of suns, and the glow of the Milky Way is billions of suns blended together. For a long time it was natural to think that whatever the universe contained, it would all be made of the same luminous material. Stars seemed fundamental, the building blocks of the cosmos. But the more astronomers measured, the clearer it became that this assumption was wrong. The universe is not made mostly of stars. The galaxies we see are not representative of the whole. The majority of matter out there is something else entirely, something invisible, something that does not shine. This realization did not come easily. For centuries, the only things we could measure in the sky were things that gave off or reflected light. Stars, planets, gas clouds, comets. Every discovery was tied to brightness in some form. By the mid-20th century, this view began to crack. Astronomers realized that if the invisible mass in galaxies and clusters were made of ordinary material, it would show itself in some way. Ordinary matter, after all, interacts with light. It absorbs, emits, scatters, or reflects. None of these effects matched the scale of the missing mass. The invisible halos of galaxies were far too large to be explained by hidden collections of ordinary stars or gas. This was a turning point. It meant the missing matter was not just faint, it was fundamentally different. It did not shine, didn't block, did not scatter. It was not made of the atoms we know, the protons and neutrons and electrons that form every familiar object. It was something else, a new category of matter. Particles we haven't met by now, the story of dark matter has narrowed to a strange place. We know it is not made of stars, not made of gas or dust. not composed of the familiar atoms that form everything around us. It reveals itself only through gravity, shaping galaxies, binding clusters, and weaving the cosmic web. But gravity alone does not tell us what it is. To understand its nature, scientists began to imagine possibilities, particles that have never been seen, particles that might exist in great abundance yet slip past us unnoticed. These are the particles we haven't met, the hypothetical building blocks of most of the universe. It can feel odd to speak about something we haven't detected as though it might be real. But this is a common path in physics. Many particles were predicted long before they were observed. The neutrino, for instance, was proposed in the 1930s to solve an energy discrepancy in radioactive decay. It seemed like a desperate idea at the time, an invisible particle carrying away missing energy. Yet decades later, neutrinos were detected, and today they are a well-established part of physics. One of the most discussed candidates is the weakly interacting massive particle, or WIMP. The name describes its key features. It would have mass, enough to contribute gravity. It would interact weakly, meaning only through the weak nuclear force and gravity, not electromagnetism. That would explain why it doesn't emit or absorb light. WIMPs could have formed in large numbers during the early universe, left over from high-energy conditions after the Big Bang. Their predicted abundance happens to match the amount of dark matter we observe. This coincidence, sometimes called the WIMP miracle, makes them a particularly attractive candidate. Listening underground. When you imagine the search for the universe's secrets, you might picture giant telescopes on mountaintops, their domes opening at night to catch faint starlight. You might think of satellites orbiting Earth, peering into deep space, or maybe enormous particle colliders, rings buried beneath cities, smashing atoms at nearly the speed of light. But some of the most ambitious hunts for dark matter are happening in quieter places, far below the ground, in laboratories carved out of mountains and mines. There, scientists are waiting in the silence, hoping to catch a rare whisper from the invisible. The reason for going underground is simple. The surface of Earth is constantly bombarded by cosmic rays, high-energy particles from space that strike the atmosphere and shower secondary particles downward. These interactions create a constant background of noise, flashes of energy that can overwhelm sensitive detectors. If you're trying to find a particle that interacts only rarely, perhaps once in months or years, you cannot afford distractions. So scientists go underground, using rock as a natural shield. The deeper you go, the fewer cosmic rays reach you, and the quieter the environment becomes. Inside these underground laboratories, massive detectors stand ready. Many of them use noble gases such as xenon or argon, cooled to liquid form. These liquids are chosen because they are chemically stable and very pure. When a particle collides with an atom in the liquid, it can produce a tiny flash of light and a faint electrical signal. Sensors surrounding the liquid are tuned to catch even the smallest event. If a dark matter particle were to strike an atom, the detector could see the result. Colliders and cosmic clues. If the underground laboratories are places of silence, patience, and waiting, then particle colliders are their opposite. Where one approach relies on stillness, the other relies on impact. Instead of listening for dark matter drifting past, colliders attempt to recreate the conditions of the early universe, smashing particles together at enormous energies to see what emerges. The two approaches could not look more different, but they share the same goal: to bring the unseen into focus. The most famous of these machines is the Large Hadron Collider, or LHC, buried beneath the border of Switzerland and France. A circular tunnel nearly 17 miles long houses powerful magnets that accelerate protons close to the speed of light. When they collide, the energy released is immense, enough to produce a shower of new particles. Surrounding detectors, themselves the size of buildings, record every fragment, every trace, as scientists sift through billions of events in search of something new: dark matter and dark energy. By now, the story of dark matter has carried us through galaxies, clusters, and the cosmic web. We've followed the evidence underground, into colliders, and across the sky. At every turn, the conclusion is the same. Something unseen outweighs the visible. But as strange as that is, the story doesn't end there. For alongside dark matter, the universe holds another mystery, one even harder to grasp. If dark matter pulls the cosmos together with its gravity, then dark energy pushes it apart. Together they form the unseen majority, two invisible presences that govern nearly everything about the universe and yet remain beyond our direct experience. Is gravity wrong? If dark matter and dark energy dominate, then perhaps our understanding of gravity itself is incomplete. Could it be that the force we think we know requires revision? Some scientists explore this possibility, developing theories that modify gravity to account for what we see. Whether those ideas succeed or not, they reflect the restless curiosity that drives the search. The universe remains larger, stranger, and more mysterious than we expect, and each step into the unseen reveals just how much more there is to learn. A universe. We barely know, for all our progress. The truth is humbling. We know more than we once did, but what we know sits like a thin layer on the surface of something far deeper. The stars, planets, gas and dust, the luminous universe, is only about 5% of what exists. The rest is dark matter and dark energy, unseen but dominant. This means that most of reality is not only invisible to our eyes, but still mysterious to our minds. The phrase, "a universe we barely know," is not exaggeration. Living in the shadows, to live in a universe where most of existence is invisible, is to accept that we dwell among shadows. The galaxies we see, the stars we name, the planets we map are only fragments. They glow brightly, yes, but they are not the whole. Around and beneath them lies the unseen scaffolding of dark matter, holding everything together. Across the vast reaches of space stretches the push of dark energy, driving the expansion faster with time. We walk through life bathed in light, yet we're carried by what we cannot see. Living in the shadows is not an exception, it is our natural condition. The night sky's secret companion. When you step outside at night and look upward, the sky feels timeless. The stars shimmer in their quiet patterns, the planets drift along their paths, and the faint arc of the Milky Way stretches across the dark. It is easy to believe that what you see is the whole story, that the glowing points and soft bands of light are all there is. But today we know there is another presence above us, one we cannot see, yet one that outweighs all the brilliance combined. The night sky has a secret companion, and it has been there all along. This companion is dark matter. It does not twinkle or shine, it leaves, no trace on our eyes or cameras. And yet it is everywhere. Each star you see is wrapped in a halo of the unseen. The Milky Way itself, with its 100 billion stars, is only the glowing skin of a far larger body, cradled by an invisible sphere of mass that extends hundreds of thousands of light years beyond the luminous disk. Every step you take beneath the stars is taken within this companion's grasp. Closing thoughts. And so we find ourselves back beneath the quiet of the night sky. We have wandered through galaxies and halos, traced the invisible web that stretches across the cosmos, and followed the clues of a universe where most of what exists is hidden. We have learned that the stars are not the whole, that the visible is only a small fraction, and that dark matter and dark energy, silent and unseen, carry the weight of reality. But this is not an ending. The mystery remains. The search continues. In the silence of underground laboratories, in the roar of colliders, in the steady gaze of telescopes watching the sky, the universe still keeps its secrets, and we are still learning how to listen. As you listen now, perhaps ready for rest, let that be a comfort. Mystery is not absence, it is presence. It means the universe is alive with possibility, larger than our understanding, deeper than our imagination. To close your eyes beneath that truth is to know that you are part of something vast, supported by what you cannot see, connected to a story still unfolding. So take a breath. Let the questions drift for now. The galaxies will continue to turn, the halos will continue to hold, the universe will continue to expand. You are safe here, resting within it. The night sky has its secret companion, and so do you. Sleep well.